Okay, so we have this problem where we're looking for the maximum positive reaction at A. And the problem, I didn't write it down, but the problem has a variety of different kind of loads, live loads and dead loads. And I'll fill those in when we get to it. So the first thing we need to do is write or draw the influence line for this. So I'm going to imagine my structure. It's fixed at C, hinge at B, and I'm going to replace A with the reaction and see what Mueller-Breslau will tell me the shape of the influence line looks like. So with this kind of a configuration, which way will this structure move, up or down? It should rotate like this. So that says that our influence line for the reaction at A should look like this. And this would be 20 feet and 15 feet. Now what we have to find is, what are these values? What is this value?
F, you mean the reaction?
And what are the values here? So what would be the in this case, the highest value would be if my unit load was at this position, x equals 0, what would be my reaction at A?
What?
1.
Say that again?
Well, remember, what's the definition of an influence line? It's the reaction of A as the unit load moves across the beam. So the largest value is when the unit load is at x equals 0. So that would be a beam that looked like...
It's like a phone call.
Yeah, somebody is getting a phone call. That looks like this. There's my unit load. And I'm trying to find the reaction at A. So I can just cut the beam here. Right? You with me so far?
Yeah.
Now, at this hinge, I would generate two unknowns, by and bx. But we're really not concerned with those right now. We're only concerned with the reaction at A. And my unit load is here. And those dimensions are 10 and 10. So I can sum moments at B, make sure this is in equilibrium, and I can find RA. So I would have a positive moment of 1 times 20 feet minus my reaction at A times 10 feet. So it looks like my reaction at A is 2. So I can come back up here and say that this is 2.
Isn't B, why is B, pinned?
No, it said B is fixed. Oh, B, I'm sorry, B is a hinge.
B is a hinge, and the problem statement says
B is pinned.
That's the same thing.
As a hinge.
A pin is a hinge. The only thing, I think that's bad terminology. I've been trying to say pin only if it's at a support. And if it's internal like this is not a supported area. This point B can move up and down.
I was thinking
But it can rotate, so that's why I call it a hinge. This is a pin.
Sure.
It can't move.
So a hinge is a pin that's not connected to...
You can call it any way you like. It doesn't matter. All you have to know is anytime you see a symbol like that, pin or hinge, no moment. I don't know what they call it. Whatever you want to call it. It doesn't matter. It has no moment. That's why when I break it apart, I don't have any moment to deal with down here. By the way, if I didn't have that, this would be an indeterminate problem and you couldn't solve it.
Let's pretend.
Of course I would. This is a perfectly valid problem.
But you would say hinge.
So let's finish it. I try to reserve the word hinge for an internal portion of a beam that does not have moment capacity. And something like this I would call a pin, or in this case I would call it a roller. I reserve the word pin support where it has both X and Y reactions. If it just has one reaction, I call that a roller. And then I call this a hinge. And I try to keep that terminology consistent. You'll get different sources will use those interchangeably, and it's okay.
So
We don't
The result is the same.
Because there's one unit load applied, and it's equidistant on both sides. We actually didn't have to do that work on RA was 2. We knew that it was going to go up 1.
Well, what you could have done is you could have gone right here over RA and known that that value is 1, and then similar triangles would have told you this was 2. But I sensed that you guys were not on to that, so I went ahead and did it this way just to show you that that's how, if you get in a jam, a pickle, I think that was the word earlier, if you get in a pickle, you can always fall back to statics. You'll find that the most fundamental thing you'll have in all of your engineering work is statics.
Yeah.
That's why we teach it to you at the beginning. And we teach it to you over and over and over. And eventually you might actually get it. Yeah, eventually. Okay, so let's finish the problem. What numbers you want to use? I'll use these numbers. So it says I have a live load of 7 kips. So my live load is 7 kips. So where do I put my 7 kips to create the largest?
I don't know.
At the
Here. So it would get a value of 2 next to it, and that would give me a reaction of 14 kips at A for that particular location.
Why do you choose that location?
It's the largest value.
Oh.
You're trying to find the maximum, right?
Okay.
The dead load in this problem is 800 pounds per foot. Yeah, I'll go ahead and change that to 0.8 kips per foot. Now, dead load you have to put across the entire structure, so you would take the total area under the influence line, both positive and negative. But there is no negative, there's only positive. So that area would be 1/2 the base, which is 20 feet, times the height, which is 2. And that looks like, what is that, 16 kips?
16. It is 16.
The live load, you're allowed to start and stop anywhere you want on the structure as long as you cover all the positive area, because we're trying to get the positive value.
Didn't we already do a live load? I'm confused.
Those are concentrated.
And it just happens to be exactly the same spot over just the first 20 feet. So the live load in this problem is 2 kips per foot.
Those are concentrated live load, correct?
Yeah, that was 7. That was a concentrated load. This is the distributed.
Okay.
I probably should have said uniform here. I'm sorry. Let me add the word uniform. I apologize for that. So then we'll have the area of the triangle, which is 1/2 the base. Oops, it's 20 feet times the height, 2. And again, that gives you, what is that? That gives you 40. So you would then add all that up. So the maximum, oops, sorry. Let me rewrite that. So the max positive reaction at A would be 70?
70.
Okay, so for the live load, the concentrate, you just put it the highest point no matter what.
Yes.
And then, so
Well, you're trying to find the maximum, so you want to use the largest value.
why do you multiply it by the? Well, I don't.
That's the way it works. Remember, superposition says that we built this based upon the fact that we have a unit load moving around.
Okay.
And this is the reaction at A as that unit load starts here at 0 and moves all the way to the end of the beam. So where's the biggest value? Well, right here. This is the actual one we solved. So when the unit load is here, it creates the largest reaction of 2. Well, our unit load is not a unit load anymore. It is 7 kips. So you multiply 7 kips times that value, 7 times 2, you get 14.
I just got it.
Okay.
So any other questions about this one?
And dead load is just the area under the whole curve.